that my tablet is plugged in. Okay, let's see. Okay, looks like my YouTube is up and running. So let me go to the PowerPoint. Okay, so good afternoon, everybody. So let's commence to a discussion of chapter 8. And in chapter 8, it's a natural follow from what we talked about in chapter 7. In chapter 7, we were introduced to certain concepts such as orbitals and the quantum numbers and so on. So now we're going to see in chapter 8 how, based on what we have covered in chapter 7, how the electrons are actually arranged in the atom, especially with respect to their energies, all right? So if you remember, we talked about the Bohr model, all right? And the Bohr model works well for one electron atoms such as hydrogens, right? It's useful to predict or explain, I should say, the type of transitions that will take place, which results in certain lines in the hydrogen spectrum, all right? But I think I made the point that that works well only for one electron atoms. I may not have gone into the exact reasons why, but the reason is right here. If you have more than one electron present, then not only do you have the interaction between the electrons and the nucleus, which is positively charged, you also have interactions between the electrons themselves, and that affects the type of spectrum that an atom will emit, and therefore it's more difficult to make any predictions or to correlate the spectrum to the electronic structure if you're using the Bohr model, all right? So that's one limitation of the Bohr model. So in the hydrogen atoms, right, what you'll find is that this is the arrangement of all the different shells and subshells, right? Remember now the formula for calculating the energy of each shell, which would be the orbit in the case of the Bohr model. In the actual modern version of the atom that we now are familiar with, we refer to shells instead of orbits, right? So this is a formula that is used to calculate the energy of each shell. So for the first shell, you have the 1s orbital here. In the second shell, you have the 2s orbital, and then you have the 2p orbitals. And then in the third shell, you have the 3s orbital, then the 3p orbitals, which appears in sets of 3s, and the 3d orbitals, which appears in sets of 5, and so on and so forth, all right? So, you know, it's very easy to basically write down or draw diagrams such as this, which gives you the relative energies of the different shells and subshells within the shell, right? So that's what happens in the case of hydrogen, all right? And here's the important point I want to make here that you should keep in mind when we look at the multi-electron atom situation. In the hydrogen atom, all the subshells of the principal shell are at the same energy level. So for example, in the second subshell, the 2s orbital and the 2p orbitals have the same energy. In the third shell, the 3s, 3p, and 3d orbitals have the same energy, and the same will be true for the 4s, 5s, etc. All right? So that's what happens in the case of the hydrogen atom. Now, if you compare the hydrogen atom in terms of the energies of the shells and subshells and compare it side by side to the typical multi-electron atom, you'll see some significant differences. In fact, there are two major differences. The first difference is that on average, all these shells here, in the case of the hydrogen atom, would be closer to the nucleus compared to when you look at the multi-electron atom compared to the hydrogen atom. So for example, the first shell here has the 1s orbital, which has an energy level at this point right here. But in the case of the multi-electron atom, the 1s, or the first shell, I should say, is of a lower energy. The same is true for the second shell when you compare the two, and the same is true for the third shell when you compare the two, right? And the simple explanation for that is that in a typical multi-electron atom, because you have more protons present in the multi-electron atom, they will pull the electrons closer to the nucleus, and therefore those shells will be more stable, or the electrons in those shells will be more stable, and therefore would have lower energy, all right? So that's one big difference between the hydrogen atom and a typical multi-electron atom. Another important difference is that in the case of the hydrogen atom, you'll notice, for example, that in the second shell, the 2s sublevel and the 2p sublevel have the same energy. But when you compare that to the multi-electron atom, you'll see that the 2s sublevel is of a lower energy compared to the 2p sublevel, all right? And you'll see a similar pattern emerging when you compare the third shell in the case of the hydrogen atom to the third shell in the case of the multi-electron atom. Again, what you'll see here is that these subshells all have the same energy in the case of the hydrogen atom, but in the case of the multi-electron atom, the 3s subshell has a lower energy compared to the 3p, which in turn has a lower energy compared to the 3d. And you see a similar pattern as you move up to the 4th, 5th, and 6th shell, all right? So those are the differences between the multi-electron atom and the hydrogen atom in terms of how the subshells are distributed in terms of energy. And therefore, it makes it a bit more difficult for us to predict the order of the energies, especially when you go up to higher shells, because what you'll see is that there'll be some overlap between lower shells and higher shells in terms of the subshells within them. But we're going to see that there's actually a way of predicting the orders of the subshells. Another thing I want to point out before we leave this page is that within each subshell, what you'll find, and this is true for the multi-electron atom, what you'll find is that the s orbitals or the s subshells will have a lower energy compared to the p subshell, which in turn will have a lower energy compared to the d subshell, which in turn will have a lower energy compared to the f subshell. So this is basically an order in terms of the energy that you'll see within every single shell which has these subshells, all right? Okay, so what else? Oh, I mentioned this already. The orbital energies are lower in the multi-electron atoms compared to the hydrogen atom. And let me see what this says. A higher number of principal shells and some shells. Okay, yeah, so I mentioned that already. There's some overlap between lower shells and higher shells in terms of the subshells within them. All right, we're gonna see some examples of that shortly, all right? So now this brings us to the topic of electron configuration. So whenever you hear or see this term electron configuration, basically what it means is how the electrons are distributed among the orbitals that are present in the atom. So there are a couple of ways we can express the electron configuration, all right? We can use what is known as the SPDF notation. And this uses numbers to designate the principal shell and the letters to identify the subshell, and a superscript number which indicates the number of electrons in the designated subshell. So you'll see something like this when it comes to the SPDF notation, right? So the way you'd interpret this here is that the 1 here represents the energy level, right? So n equal 1, 2, 3, whatever. The S here represents, of course, the subshell, and this 2 here written as a superscript represents the number of electrons within that subshell. So basically, the way you'd interpret this is that in the first shell, it has this S subshell, which has 2 electrons in it, all right? So we use this representation basically to show you how the electrons are distributed within a particular atom, all right? And we're gonna see some more examples of that. Another way of representing the electron configuration is using what are known as orbital diagrams. And what you see on the screen here is an example of that. So in some textbooks, they call this electrons in boxes, right? Basically, it's the same thing. And basically, the boxes represents the different orbitals themselves, and the arrows represents the electrons. And you'll notice that if you have 2 arrows occupying the same box, the arrows are spinning in the opposite direction, right? We're going to talk about the significance of that shortly, all right? But basically, this is the electron configuration, or this represents, I should say, the electron configuration of a particular atom. So the way you'd interpret this is that in the first energy level, you have the 1s subshell. There are 2 electrons occupying that subshell. In the second energy level, or the second shell, you have 2 subshells. You have the 2s and the 2p. In the 2s subshell, you have 2 electrons spinning in opposite directions. And finally, in the 2p subshells, you have 3 electrons, each occupying an individual subshell, and they're all spinning in the same direction, all right? So that's basically how you'd interpret this representation. Now, the advantage of using the orbital diagram, as opposed to the SPDF notation, which I showed you before, is that this gives you a better picture in terms of how the electrons are distributed. It tells you basically that the electrons are occupying specific orbitals, and also it tells you about the electron spin within these orbitals for the electrons that are occupying them. So we're going to see the significance of that also later on, all right? Okay, okay, so that's just saying what I just said before. Okay, so let's talk about the rules for electronic configurations in atoms. There are some rules that you have to follow in terms of determining the electron configurations of atoms. And this is important because it turns out that the electron configuration of atoms influence properties displayed by the elements or by the atoms. It tells you, for example, whether or not the atom can form ions. It tells you about whether or not the atom can display certain magnetic properties. So there are several things that, you know, can be predicted if you know what the electronic configuration, even the position of the elements within the periodic table themselves is as a result of the electronic configurations, right? So based on the electronic configurations, you can tell something about where exactly in the periodic table a particular element will occupy, and vice versa. If you know where the element is positioned in the periodic table, you can come to some conclusion about the electron configuration. So it's very important that you know and understand the rules for determining the electron configurations of atoms, all right? So first thing you want to mention here is that electrons will occupy the lowest available energy orbitals in the ground state configuration. If you remember, we said earlier, the ground state configuration is the most stable, or the ground state, I should say, generally speaking, is the most stable or lowest energy state. So therefore, when we're talking about the ground state configuration, we're talking about a situation where the electrons will occupy the lowest available energy orbitals in that configuration, all right? So for example, in this particular case here, this is the electronic configuration of a particular element. In fact, let me see here, 1, 2, 3, 4, 5, 6. So this would be the electronic configuration of carbon, all right? Now, this configuration is, and I should have made a correction here. It's not actually incorrect. It would be incorrect if we're talking about the ground state configuration. This configuration can actually exist, but it would not be the ground state configuration, which is the focus of our discussion here, right? So more accurately, we should say that this is not a ground state configuration. Why? Because in this configuration, you have two electrons occupying the same orbital. One thing you should remember about electrons is that they carry negative charges, and like charges repel, right? So therefore, there will be some repulsive forces that would take place when you have two electrons occupying the same orbital, all right? So basically, this would not be the correct electron configuration. In fact, let me see here. The correct electron configuration would be where this arrow would not be here, and an arrow would be here, right? And that would be the ground state configuration, all right? The electrons would prefer to spread. I'm sorry, yes, sir. Oh, I just realized I made a mistake. I'm sorry. You were saying, sorry.
Wouldn't it fill the 2s orbital first?
Yes, I just realized that. So let me erase this here. I just realized. Thank you for pointing that out. Yeah, so in actual fact, what you just said is correct. Let me get back my pen function here. I wasn't paying attention to the lower orbital, so let me go back to the pen function. Okay, so in effect, what will happen is that the more stable configuration would be where this electron will not be here, but you'll have an electron here, right? So that would be the ground state. So ground state configuration. That would be the ground state configuration, all right? And that's because the electrons would prefer to crowd into the lower orbital, the lower energy orbital or subshell before going into the higher subshell, all right? So this would be the ground state configuration. Yes, sir.
In this case, so instead of the orbitals filling one electron and then two electrons in each box, it would fill all of the available boxes with one electron and then go back and start filling the second slot in each box?
Right, exactly. You start from the lowest energy first. So the first 2 electrons will go into the 1s orbital, and then the next 2 electrons will go into the 2s orbital, and then the next 2 electrons will go into the 2p orbital, with each orbital being singly occupied. You see what I'm saying?
Okay, all right.
So
that makes sense.
Yeah, so that would be, excuse me, that would be the most stable configuration, right? Okay,
Right.
so let's talk about this important rule, the Pauli exclusion principle. And this rule says no 2 electrons in the same atom may have the same 4 quantum numbers. And basically what that means is that in any electron configuration, and it doesn't matter if it's ground state or not, each orbital can only have a maximum of 2 electrons. And not only that, the 2 electrons occupying the same orbital must have opposite spins, all right? So that's basically what Pauli's exclusion principle concludes, right? That each orbital must have a maximum, can have no more than 2 electrons, and where you have 2 electrons occupying the same orbital, those electrons must be spinning in the opposite direction, all right? Let me see if I have an example of this here. No, I don't. But actually what we have here is an example, right? So you notice here that you have 2 electrons in the 1s sublevel. And as you can see, they're spinning in opposite directions. And you have 2 electrons here in the 2s sublevel, and they're occupying the, they're spinning in different directions, right? So what would be impossible according to Pauli's exclusion principle is something like this, where you have 2 electrons in the same subshell, or same orbital, I should say, and they're spinning in the same direction. And there's actually a reason for that, basically, and it has something to do with physics and electromagnetism and so on. Basically, the reason for that is that when you have electrons spinning in opposite directions, they generate magnetic fields which will result in the electrons being attracted to each other. If they're spinning in the same direction, then basically they're generating magnetic fields which will repel each other. So therefore, you won't have this situation here where 2 electrons are occupying the same orbital and they're spinning in the same direction. That's just a basic short summary of the reason why. I mean, it's more complicated, but that's basically a summary of the reason why you can't have 2 electrons occupying the same orbital and spinning in the same direction. All right, so that's basically the Pauli exclusion principle. Okay, moving along. Okay, so for orbitals of identical energy, electrons enter the empty orbitals whenever possible. And that is basically what we call Hund's rule, right? So basically, according to Hund's rule, this would not be the ground state configuration, right? The ground state configuration would be where instead of occupying this place here, this electron would instead basically occupy the vacant orbital in the 2p sublevel. And not only that, this electron must be spinning in the same direction as the other 2 electrons in the same sublevel. So this would be the ground state configuration for this particular atom, which is what? 1, 2, 3, 4, 5, 6, 7. That's nitrogen, right? So this would be the electronic config, the ground state configuration for nitrogen, all right? So that's what Hund's rule says. Hund's rule basically says that for orbitals of identical energies, such as this 2p sublevel here, the electrons will basically try to spread out themselves among the vacant orbitals whenever possible. Now, there are some cases where it's not possible. For example, if in the case of the next element, which is oxygen, then this electron here, let me erase this here. Let me, in the case of oxygen, then this electron here would have to pair up with any one of these electrons already present in the 2p sublevel, all right? So that's basically Hund's rule. Okay, let me go back to my pen function. Okay, what else? So electrons in half-filled suborbitals or sublevels must have parallel spins, all right, in the ground state configuration, which is the point I was making earlier when I put this particular electron here. This must be spinning in the same direction as the other two electrons, which were already occupying other 2p sublevels separately, all right? So this would not be the ground state configuration for nitrogen, right? Because this electron here is spinning in the opposite direction compared to these two electrons already occupying the 2p sublevel, right? So this would be an excited state configuration. It's not the lowest energy configuration. All right? So that's basically how Hund's rule works, all right? Okay, any questions about Hund's rule? Any questions?
No, I don't believe so. But this makes a lot more sense than when I first went over it.
Yeah, it's like I said before, well, when I started the previous chapter, and that is so true again for this chapter, this particular area is very abstract, very abstract. It's an important area of chemistry. I won't deny that, but it's very abstract. And I remember when I was a student, I struggled with this mightily. I mean, it wasn't until I think my second year in college that I gained a sense of how important it was when we had to do actual calculations of shapes of orbitals and so on. But don't ask me to remember those things because I've forgotten all about that. Okay, so let me move on now. So this is a summary of the type of occupancy of the different orbitals and subshells and so on. I think we went through something like this before, or maybe I'm confusing you guys with the intro class. Anyway, basically starting from here, for the first shell where n is equal to 1, if you remember what we talked about in the previous chapter, the only possible value of L would be 0. So therefore the subshell designation would be S. And of course you would know that there's only one type of S orbital that is present in any sublevel. The maximum capacity would be 2 electrons, and the principal shell capacity would be 2 as well, since that's the only sublevel within that shell. When you get to n equal 2, there are 2 possible values of L, 0 and 1. The designations correspondingly would be S for the 0, P for the 1. And in terms of the number of subshells or orbitals within the subshell, for S it's 1, for P they come in sets of 3s. In terms of the occupancy, the maximum capacity would be 2 for the S orbital, 6 for the P orbital, and therefore the total capacity for the n equal 2 shell would be 8. And then you can, of course, rationalize what happens for the third and the fourth shell and beyond, all right? Okay, so if you remember, I said that it becomes more complex as you move up in energy for the different shells, and therefore it makes it very difficult to make predictions as to the actual order of the orbitals in terms of energy within any atom, right? Well, not any atom actually, any multi-electron atom. So basically, this diagram that you see on the screen is basically the order, well, not the order, but it's a guide for helping you to determine the order of the energies of the orbitals in an atom, all right? So basically what you do, I remember when I was a student, the way I would remember this diagram is that I would get a sheet of paper and I would write down 1s, 2s, 3s, all the way down to 7s. And then I'll start at the second shell here, 2p, 3p, 4p, 5p, all the way down to 7p. And then I'll start at the third shell here to take care of the d orbitals, 3d, 4d, 5d, 6d. And then at the fourth shell, I'll start with the 4f orbitals, 4f, 5f. You could actually go further, but for our purposes, we don't need to go beyond the f subshell for any of the shells, all right? Which would be the fourth and fifth shell and beyond, all right? And then you draw your arrows. That's what I would do. I would draw the arrows as seen here. And then basically to establish the orders of the energies of the different subshells, I would follow each arrow from tail to head. So basically based on this here, the order of the orbitals, let me squeeze it here, would be the first orbital or the first subshell would be 1s, then 2s, then 2p, then 3s, then 3p, then 4s, and so on and so forth. You just basically follow from from tail to head, then tail to head, then tail to head, and so on and so forth. And therefore you can get the order of the orbitals in terms of their energies, all right? So yeah, I would strongly recommend that you basically know how to use this particular diagram in order for you to get the correct order of the sublevels, right? So now we're going to get into what we call the Aufbau principle, which is based on what I just showed you, the diagram I just showed you. The Aufbau principle is basically how you would determine the electronic configuration of any atom, literally any atom that you can identify in the periodic table. The word Aufbau, I think it's a German term, if I'm not mistaken, which basically means building up. So basically what we're referring to when we talk about the Aufbau principle is the hypothetical building up of an atom from the one that precedes it in the atomic number. So if you start off with the first element in the periodic table, which is of course hydrogen, the electronic configuration is 1s1, right? Which means that the first electron will go simply into the 1s sublevel because that's the lowest energy level, right? Then we get to helium, which means that to get from hydrogen to helium, you simply add one electron to this, and now you have 2 electrons occupying the 1s sublevel, all right? And then to go from helium to lithium, you add 1 electron, but that electron cannot be occupying the 1s sublevel because the 1s sublevel is already full, right? Remember, each orbital can have a maximum of 2 electrons. So therefore the s orbital here cannot have more than 2 electrons. So therefore the next electron that's added will be added to the next sublevel, which would be the 2s sublevel. So this would represent the electronic configuration of the next element, which is lithium, all right? And if you continue with that same process, you can generate the electronic configuration of pretty much any atom with a few exceptions, which we'll get into shortly, right? Now, before we get into that, I want to point out something here where this here, this here, all these examples that we have looked at so far are what we call oh gosh, I forgot the term. The complete electron configuration of the atom, all right? But there's another way of representing the electron configuration of the atom, which is more abbreviated, and we call it the abbreviated electronic configuration, right? Now, how do we get from the complete configuration to the abbreviated? Well, what you'd have to do is first identify the group 8 element that precedes the element that you're concerned with in the periodic table. So in this case, if we want to write down the abbreviated version of this configuration, we go to the periodic table and we look for the group 8 element that comes before lithium, and that would be helium. Now, in the case of helium, as we saw here, the electronic configuration of helium is 1s2, which is a part of the electronic configuration of lithium. So to get the abbreviated version, what you do is replace the 1s2 with the symbol of helium within parentheses. In other words, we write it like this. So the 1s2 here, the 1s2 here that you can identify in the electron configuration of lithium is replaced by the symbol of helium within parentheses, and then you write down what is left after that, which is the 2s1. So this would be the abbreviated electron configuration, and this is the complete electron configuration, all right? Now, you might wonder, why do we need the abbreviated version? Because after all, when you compare this to this, there's not much difference between these two in terms of the length of characters needed. Well, in the case of larger atoms, it can make a difference in terms of how many characters needed in order to write down the complete versus the abbreviated. So as an example, I'm going to use sodium. Now, sodium has an atomic number of 11, all right? So if you were to write down the complete electron configuration of sodium, it's going to be 1s2, 2s2, 2p6, 3s1, all right? So that would be the complete unabbreviated electron configuration for sodium. Now, to get to the abbreviated version, what we have to do is consult the periodic table to see which element precedes it in the periodic table. So if you go to the periodic table, you'll see that the element that comes before sodium is neon. The electronic configuration of neon, which has an atomic number of 10, would be 1s2, 2s2, 2p6, all right? So if you compare neon to sodium, you see that what they have in common is this part right here, right? 1s2, 2s2, 2p6. So therefore, to get the abbreviated version, what you do is replace this circled part here with the symbol of neon in parentheses. So the abbreviated electron configuration would be Ne in parentheses, followed by 3s1. And of course, if you compare this to this, you see that this representation is a lot less smaller, less characters needed, right? And therefore, in some situations, this would be convenient in terms of representing the electron configuration of sodium, right? And you'll see, even for larger atoms, you can do the same thing, and you'll recognize the convenience of using the abbreviated electron configuration in those situations, all right? Okay, any questions about this? Any questions? Any questions?
No, not for me.
Okay, so here are some other examples, and I just remember there's an error in one or some of them. I don't remember which one, but anyway. Let's start off with this one here, carbon, atomic number 6. This would be the electronic configuration according to the SPDF notation, and this would be the electronic configuration according to the electrons in box or orbital diagram notation. And in terms of the abbreviated electronic configuration, it's going to be this, what you see here, right? Now, of course, this here represents the electronic configuration of helium, which is this part right here, or this part right here. And then you just simply write down the rest, which is 2s2, 2p2, all right? Here's another example. Going from carbon to nitrogen, we simply add 1 electron. So that 1 electron will enter the 2p sublevel. So you're going to get this here, or you're going to get this here. And that changes, of course, the abbreviated version to this right here. And then you should be able to follow what happens when you jump to the next element, which is oxygen. Again, you just add an electron, which will be added to the 2p sublevel. You'll notice, of course, in the orbital diagram that the next electron is added to any one of these 2p sublevels, but that electron must be spinning in the opposite direction. And the resulting abbreviated electron configuration is shown here, and so on and so forth. When you get to fluorine, this becomes 2p5 because you add 1 electron again to the 2p sublevel. You end up with this, and you end up with this. And then when you get to neon, you end up with 2p6 here, which means that this is completely filled, and you end up with this sublevel here. And that's basically how that is done. All right. I thought there was an error here, but maybe not. So I may have changed it. Yeah, I think I've corrected it. Okay, so any questions about these examples? Any questions? Any questions?
Is the reason that fluorine is fluorine and the other halogens in general, the reason that they're so reactive is that they've only got 1 electron slot?
Yeah, exactly.
Before they have a stable
exactly.
electron configuration.
Right. Yeah, we're going to get to that later on. But since you asked, basically for elements in the A group regions, right? So we're talking about elements from 1A, 2A, 3A, all the way to 7A. They tend to either lose electrons or gain electrons in order to obtain a full outer shell, which is usually an octet with the exception of hydrogen, which would be a duet, right? So in the case of fluorine, fluorine needs only 1 electron in order to get a full octet. The octet would be the 8 electrons in the outermost shell, the valence shell, which would be, in this case, the second shell, right? And that's why fluorine, that's one of the reasons, I should say, why fluorine is reactive, because it will need just 1 electron to get the full outer shell, which will be more stable. There are other reasons why too. For example, the fact that the second shell is very close to the nucleus. So therefore, there'll be a pull of the nucleus to, well, the attraction between the nucleus and the valence shell electrons will be stronger, and therefore the electrons would be more stable in the formation of the fluoride ion. So that's another reason why. But what you just said is, you know, one of the reasons why fluorine is a very reactive gas, especially when exposed to metals, right? They react very quickly with metals. If you have a, what do you call it now? If you have a flask with fluorine gas, and if you add a drop of, I mean, not a drop, but a piece of very reactive sodium or even more reactive potassium, you're going to get a very explosive reaction. That reaction would have to be taken for precaution reason. You'd have to take, that reaction would have to take place behind some protective shield or something like that, because the amount of heat and light generated would be very great. Let's put it that way. All right. Okay. So, oh, I'm sorry. Yes, sir. Got a question?
Fluorine like isn't it the most reactive element in some cases?
I know it's the most reactive halogen. And I think it's also the most reactive nonmetal. But to be perfectly honest, I'm not sure if it is the most reactive element, because the group 1A metals, especially the ones further down that group, are very reactive. So to be perfectly honest, I don't know which one reacts faster, but I think I would actually go out on a limb and say that fluorine is the most reactive nonmetal.
Okay.
Okay, so let's talk about the main group elements versus the transition elements in terms of the electron configuration. So what you'll find is that when you apply the Aufbau process to elements in the group A region, which is the main group elements region, then the electrons basically will be added to either the S or P orbitals, all right? So the A group, those are the A group elements. Excuse me. Ooh. The first 20 elements, of course, are all main group elements. So we're talking about elements starting from hydrogen to calcium, all right? And then we have a second category of elements known as transition elements, right? And in the case of these elements, as you go from one to the other using the Aufbau process, you'll be adding an electron to an inner principal shell, all right? And we're going to see that shortly. So in the case of the A group elements, you're adding electrons to the S or P orbitals in the outermost shell, right? But in the case of the transition elements, the electrons are being added to an inner shell, all right? And we're going to see that at work later on. In fact, it says here that the fourth period transition elements will have N = 4 as their outermost shell, but the electrons are being added to the 3D subshell, which is of a lower energy level in terms of the shell from which these subshells are located. Okay, so that's what's seen here. Now here we're talking about the fourth period, right? Now the fourth period has, to begin with, potassium followed by calcium. And then the next element here would be scandium, all right? So in the case of scandium, you have the electronic configuration of argon. So we're talking about the abbreviated version here. And one electron will be occupying one of the 5 3D orbitals. And then when you get to the next element, titanium, you just add an electron to this to get this, all right? And hold on, there is, okay. There's an error here. Let me just point it out first before I continue with the Aufbau process here. And I should have corrected this. You'll notice that in each of these cases, you have 3D1 first before 4s2, right? That is not the correct order, right? Because if you go back to the diagram I showed you, let me go back to this diagram here, right? You see that 4s comes before 3d, all right? So the correct order would be 4s first, followed by 3d. So let me go back to this here. So this should be actually 4s2 followed by 3d1, 4s2 followed by 3d2, and so on. 4s comes before the 3d, all right? So please make a note of that. Okay, so as I was saying, this would be the electron configuration of scandium, and then you add one electron to scandium to get the electron configuration of titanium, which is this, right? And then you get the vanadium, You add one electron here and you get this, right? So as you can see, in each case, you're adding an electron to a singly occupied orbital. Now, based on what we have learned so far, and I would not blame you for even believing this or thinking this, to get from vanadium to chromium, one would think that what you need to do is add an electron here. To get from vanadium to chromium, you add an electron here, all right? And that would be the electronic configuration for chromium. But it turns out, and there's a long story behind this, which I don't want to get into, but it turns out that this would not be the correct electron configuration, or I should say, not the most stable electron configuration for chromium. It turns out that the correct electron configuration for chromium is shown right here. And as I said before, there's a long story behind that. But basically it has to do with the fact that this electron configuration here is more stable because these 5d orbitals are singly occupied and this 4s orbital is also singly occupied. So therefore there's some stability that's associated with half-filled sublevels, all right? So as stated here, half-filled sublevels are more energetically favored when it comes to their configurations, all right? So chromium has this electronic configuration where it is the electron configuration of argon, then 4s1 3d5, all right? Okay, and then from chromium to manganese, you simply add an electron here to get this, all right? So one electron is added here and you get this, okay? And then you continue to add electrons. Now this time what will happen is that you're going to have pairing of electrons as you go from manganese to iron. So basically one electron will be added to this orbital here this orbital here to get this, and then to go from here to here, an electron is added here to get this, and then to go from here to here, an electron is added here to get this, all right? And again, when you go from nickel to copper, there's something unusual that happens again. What you'll notice, or what you might think, is that the next electron will be added here. Well, it turns out that in actual fact, what happens is that not only would you have an electron added here, but one of these two electrons instead would go into this orbital, and you're going to end up with this here as the correct electron configuration for copper. And the reason for that is that not only is half-filled sublevels more stable, but also completely filled sublevel, along with half-filled sublevels, will have a more stable configuration. So as you can see here, the 3D sublevel is completely filled, the 4s sublevel is half-filled, and therefore that is more stable than what you'd expect, all right? So therefore the most stable electron configuration is this right here. The electron configuration of argon along with 4s1 3d10, all right? Okay, and then of course to get from copper to zinc, you simply add an electron here, and that gives you the electron configuration for zinc, all right? So that's basically how the Aufbau principle works when you get to the transition elements region, all right? And that's true not only for period 4, but what you see a parallel situation for elements in periods 5 and below, all right? Okay, any questions about this? Any questions about the Aufbau principle applied to transition elements?
Not I.
Okay, so moving along. So the result of the Aufbau principle will give you, of course, well, one of the consequences, as I mentioned before, is that the Aufbau principle, or I should say the electron configurations of atoms, actually determines the positions of the elements in the periodic table, right? So what you see here on the screen, and this seems a bit small, I don't know if you can see it on your screen, but if you look at it closely, what it is showing you is the electronic configuration for each element within each box for each element. It gives you the electron configuration of the outermost shell of the atom. Now, by definition, the outermost occupied shell is called the valence shell of the atom, all right? And it turns out that based on the electronic configuration, the period number is equal to the principal quantum number of the electrons in the valence shell, right? So if you remember, the period numbers would basically be the numbers for the rows, right? So for the first row, the period number is 1. For the second row, the period number is 2. For the third row, the period number is 3, and so on and so forth, right? So if you look at if you choose any element, right, and you look at the number of electrons in the valence shell, then you'll see that that number will be equal to the period number for that element. So if I were to choose, for example, tin, right? Tin has a total of 2 plus 2, 4 electrons in the valence shell. And if you look here, it's in period 4. 1, 2, 3. I'm sorry, I made a mistake. The valence shell is related to the group number. Oh, okay, I'm so sorry, folks. I'm mixing up the group number with the period number. So let me restart again, I'm sorry. Okay, the period number represents the quantum number of the electrons in the valence shell, not the number of electrons in the valence shell, all right? So for example, going back to the tin example, the highest occupied shell, the valence shell, is the 5th shell. So therefore 10 has a period number or belongs to the period with the period number 5, all right? Or if I were to choose another element, let's say rhodium, right? You'll notice that the highest occupied shell here is the 5th shell. So therefore it belongs to period 5. Or if I look at sodium, the highest occupied shell for sodium is the 3rd shell. So therefore it belongs to period 3, all right? So basically the valence shell number or the N number for the valence shell would be equal to the period number, all right? Okay, so that's one consequence of the electron configuration. It gives you basically the period to which the particular element belongs based on the number of the principal quantum number of the valence shell. Okay, and then when it comes to the actual number of electrons in the valence shell, that's where the group number comes in, especially for the A group elements. Now, what I'm about to say will apply only to the A group elements. It will not apply to the elements in the transition region, right? So basically, for the main group elements, the number of valence shell in electrons is the same as the group number, right? For that element. So for example, if I were to choose bromine, right? Bromine has a total of 7 electrons in its outer shell, in its valence shell. So therefore it belongs to group 7A. If you look at, let's say, tin again, it has 4 electrons in the valence shell. So therefore its group number would be 4A. If I look at, let's say, strontium, it has only 2 electrons in its valence shell. So therefore it belongs to group 2A, and so on and so forth. So this only applies, as I said before, to the A group elements. It does not apply to the elements in the transition regions here or the inner transition regions here. All right, things are a bit more complicated when it comes to those elements. All right. Okay, so what you see here is basically a summary of the different blocks, as we call them, with respect to the Aufbau principle, right? As you go from one element to the next across any period, right? So the S block elements, let's start off with this here. As you go from one element to the next across any period, what you'll be finding is that you will have to add an electron to an S sublevel, right? So to go from, let's say, lithium to sodium, no, lithium to, oh gosh, I'm blanking. Hydrogen, helium, lithium.
Beryllium.
Beryllium, I'm sorry, yes, thank you. As you go from lithium to beryllium, you're adding an electron to a S sublevel. Same thing is true here if you're going from sodium to magnesium and so on and so forth, right? So that region here is called the S block. And then over here, in the P block elements, as you go from one element to the next, you're adding an electron to a P sublevel, right? So for example, boron, as you go from boron to carbon, to nitrogen, to oxygen, to fluorine, you're adding an electron to the 2p sublevel. And the same is true for the 3p sublevel and so on and so forth. So we call this region the P block region, or P block, P block region of the periodic table. And then here in the inner transition elements, or I should say transition elements, as you go from one element to the next, you're adding an electron to a D sublevel. So for example, here you have scandium. As you go from scandium to titanium, to vanadium, to chromium, etc., you're adding an electron to the 3D sublevel, all right? So we call this region here the D block region, and then as far as the inner transition elements are concerned, we call this the F block region, all right? So those are just some different regions where they're categorized according to which orbital will be gaining electrons as you're applying the Aufbau principle going from left to right of any period within these blocks, all right? Okay, so now we're going to get into, I think we're going to get into something kind of like what you were talking about with respect to fluorine, the question that you asked. We know what the valence electrons are, right? The valence electrons we just defined. These are the electrons that occupy the highest energy shell, right? So for example, if you look at the electronic configuration of sulfur, which is represented here and here, we can easily identify the valence electrons. The valence electrons will be occupying the shell with the highest N value, which would be the shell which has the 3s and 3p subshells. So the total number of valence electrons here would be 6, 4 plus 2, 4 plus 2, right? So sulfur has 6 valence electrons, and as such, it belongs to group 6a, right? Also important, we need to be able to identify what are known as the core electrons. Basically, the core electrons are those electrons that are not the valence electrons, right? They're found more closer to the nucleus, right? So in the case of sulfur, as you can see from the electronic configuration here, the number of valence electrons, or I should say core electrons, would be 10, right? So basically the number of core electrons plus the number of valence electrons would simply give you the total number of electrons present within any atom, all right? So it's very important that you be able to identify the valence electrons as opposed to the core electrons, all right? Now that's important because that would help you to determine the electron configurations of ions. So this is something that is new because I don't think you would have learned this in your introductory or high school chemistry. Typically in high school chemistry or introductory chemistry, you would learn about determining the electronic configuration of atoms, but you would not learn about how to determine the electron configuration of ions. So that's what we're going to be discussing right now. So let's talk about the electronic configuration of monatomic anions. Of course, we know that to get from an atom to a monatomic ion, we simply add electrons so that the anion will end up with a full valence shell. So for example, in the case of chlorine, this would be the full electron configuration of chlorine. And as you mentioned before, in the case of fluorine, chlorine is very similar because chlorine has basically one p orbital here in the 3p sublevel that is half occupied. So therefore it can accommodate an extra electron, right? So when the chlorine atom becomes a chloride ion, then what happens, and I need to write this in because it's not clear here. So you're adding an electron to the chlorine atom here. So that means that that electron will simply go into the 3p orbital like that. Of course, that electron will be spinning in the opposite direction. And now we have the electronic configuration of the chloride ion, right? So this is a chlorine atom, electron configuration, and this is a chloride ion electron configuration, all right? Alternatively, we could write the configuration for the chlorine atom as 1s2, 2s2, 2p6, 3s2, 3p5. In the case of the chloride ion, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, all right? So that's the electronic configuration of the chloride ion. And if you are observant enough, you'd realize that this would be the same as the electronic configuration of neon, whoops, right? So the electronic configuration of the chloride ion would be the same as the electron configuration of neon, right? Now, it does not mean that, oh, you had a question?
Wouldn't that be the electron configuration of argon?
I'm sorry, you're right, argon, my bad. You're right,
Okay,
thank you. Thank you
cool.
for pointing that out. So let
No, you're
me,
fine.
yeah, I'm thinking of fluoride to fluorine to fluoride. So let me do this here. So this here would be argon. Thank you for pointing that out. Now, very important point here is that we're not saying that chloride becomes argon, right? Because these are two different elements. We know they're two different elements because the chloride will still have 17 protons, while the argon will have 18 protons. So therefore, they're obviously not the same element. All we're saying is that the electronic configuration of the chloride ion is the same as the electron configuration of the argon atom, all right? And there's a term for, I think we're going to meet that term later on, but I'll just mention it now. There's a term for species that have the same electron count. They're said to be isoelectronic. So when we say two species electronic, when we say two species are isoelectronic, we're saying basically that they have the same number of electrons. So the argon here atom is isoelectronic with the chloride ion. All right. Okay. Any questions about this? Any questions about electron configurations of anions?
No, I don't think
Okay.
so.
All right. So let's look at the electronic configurations of cations. Now, in this case, you have to be a bit careful, especially when you get to the transition region. But before we get to that, let's talk about what happens for A group elements. So we know that cations lose electrons so as to end up with a valence shell, which is complete 8 electrons, right? So an example of this would be sodium. Sodium has an atomic number of 11, and this would be the electronic configuration, right? So to get from sodium atom to the sodium cation, an electron will be lost. This would be the electron that is lost, right? And therefore, this would be the result, right? So therefore, actually, when the electron is lost, the orbital disappears. That orbital does not exist anymore. So basically, the electronic configuration of sodium is 1s2, 2s2, 2p6, right? 3s1. But in the case of this anion here, let me write it here, the electronic configuration is going to be 1s2, 2s2, 2p6. And this is actually the electronic configuration identical to neon, right? So the electronic configuration of sodium, I'm sorry, is identical to that of neon, right? Again, that doesn't mean that sodium becomes neon, because in this case here, sodium has 11 protons, while neon has 10 protons, right? So basically they have the same number of electrons. So again, sodium and neon are said to be isoelectronic, all right? Okay, now, oh, you had a question? Yes, sir.
The noble gases, that's what they're called. Do the noble gases, are they monatomic or do they bind
exist
together?
No, they don't bind together. They're monatomic because they're already stable as atoms. They all have 8 electrons on their outer shell. So they have very little tendency to form compounds because they're already satisfied with their octet. In fact, for helium and neon, as far as I know, and I probably need to check up on this, but last I saw, nobody has been able to make any compounds with helium or neon because they're so stable, right? Now, for the other elements, for the other elements below neon, chemists have been successful in making compounds, but they have to apply some extreme conditions in order to make those compounds and for those compounds to basically remain intact. If those compounds are exposed to regular atmospheric conditions, room temperature conditions, whatever, they basically come apart. All right. So that's basically a summary of how stable those elements are, primarily because they're totally satisfied with having 8 electrons on their outer shell, and therefore they don't have any need to combine with anything else. All right.
All right.
Okay.
All right.
So what I just described is for A group elements which lose electrons to form monatomic ions. Now, when it comes to transition elements, you have to be a bit more careful, right? And this is where the order of the orbitals become really important in terms of predicting what the electronic configuration of an ion is. Remember, whenever cations are formed, electrons are lost. And this is the important point here. In fact, let me underline it here for emphasis. The important point here is this: when the electrons are lost, they are lost from the highest principal energy level. All right. So let me explain what I mean by this. So let me choose an element. Which one from this region? Let me choose chromium. So let me get out of this here and get to my writing pad. Where's the writing pad? Oh, here it is. And let me just clean this up. No. Okay. So chromium. Okay, so let me see. What's the atomic number of chromium? Let me get I can find my periodic table here. Oh, here it is. Chromium.
Oh, it's 24.
Chromium has an atomic number of 24. Exactly. Okay, so atomic number 24, which means that it has 24 electrons, the atom, right? So if I were to write down the full electronic configuration of chromium, it's going to be 1s2, 2s2, 2p6, 3s2, 3p, I'm sorry, what am I doing? 3p6, wait a minute, 3p6, that's 4s2, so that's 20, and then 3d4. Let me check and make sure. So that's 10, 12, 18, 20, 24. Okay, good. So this would be the full electronic configuration of chromium, right? For the chromium atom. Now, let's say you want to form the chromium 3 ion, so Cr3+. In order for you to do that, you'd have to subtract or lose 3 electrons from the chromium atom, right? Now, you might be tempted, and I can completely understand why, you might be tempted to start subtracting electrons from here, right? But let me go back to the slide which I just left. Remember what we said? We start to lose electrons from the highest principal energy level. So going back to this here, the highest principal energy level would be the 4th energy level, right? Not the 3rd energy level. So therefore you would start removing electrons, you'd start removing electrons from here, right? So you're going to lose these 2 electrons here, and this here would be reduced from 4 to 3, because remember, we're removing a total of 3 electrons. So the electronic configuration for chromium 3+ would be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d3. All right? Or if you want to write down the abbreviated version, this would be, let me see here. This would be
argon, I think.
Argon, and then 3d3. All right? So that would be the electronic configuration of chromium 3+. All right? So please note, whenever you're removing electrons, especially when it comes to the transition region or inner transition region, you start removing electrons from the subshells with the highest n value or principal quantum number. And then if you need to remove 4, or I should say, if you need to remove more, then you start removing electrons from the next highest orbital or energy level, and then you continue along the line. All right? So that is something that you have to be really careful, because students tend to make a lot of errors when it comes to determining the electron configuration of ions. All right. Okay. Any questions about this discussion of determining the electron configuration of cations. Any questions? Any questions?
No, I don't think so.
Okay, so moving along. Okay, so what you see here is basically, you know, the electronic configurations resulting from removing electrons from elements in that region. So the chromium 3+ is what we did here, right? And if you carry out the same exercise, you can do this on your own. If you have any problems, just let me know. But you can figure out the electronic configurations of these others, which would be these here. So you can try it on your own. Try to figure out the electron configuration of, let's say, chromium 2+, manganese 2+, Fe3+, whatever, and compare your answers to what you have here so that you can see how you can determine the electron configurations of elements in that region. Okay, what next? I think this will be the very last topic for today. So let's talk about magnetic properties, another consequence of the electronic configurations of elements. There are three main types of magnetic properties displayed by elements. You have what is known as diamagnetism, which is the weak repulsion associated with paired electrons. Then you have paramagnetism, which is the attraction associated with unpaired electrons. And then you have ferromagnetism, which is the exceptionally strong attraction of a magnetic field for iron and a few other substances. Now, the focus of our discussion when it comes to magnetic properties will be paramagnetism, all right? We're going to look at the fact that if you have an electronic structure where you have unpaired electrons, then you can actually observe this particular phenomenon, all right? Now, what I'm going to show you here, and I hope the volume comes across. I have to take out my earpiece here to do this. I'm going to show you a video. Okay, okay, let me plug this out for the time being. Okay, let me escape this. Okay, what I'm going to do is copy and paste this URL here. And this is basically a demonstration of paramagnetism this. It's a YouTube video.
Theater presents Gold Guts.
Okay, hold on 1 minute.
Just science. Hi, I'm Joanne.
Let me make sure you guys can hear this.
Oh, we can hear it fine.
Oh, okay.
It's coming across good.
You can hear it?
Test tube of liquid nitrogen.
And this is a test tube of liquid oxygen.
Let's see what happens when we pour the liquid past the poles of a strong magnet.
Okay.
Now, liquid nitrogen isn't normally magnetic, but each of the nitrogen molecules acts like a tiny magnet when it's exposed to a magnetic field. This effect is known as diamagnetism. That's just a fancy way of saying that each of the nitrogen molecules is repelled by the magnet's magnetic field. So, when I pour the liquid nitrogen past the magnet's poles, it doesn't look like anything special happens. The nitrogen just falls past the magnet. That's because the diamagnetic effect is very weak, so we don't normally observe it. All materials are at least slightly diamagnetic, but because the effect is so tiny, we don't normally notice it.
Just like nitrogen, oxygen isn't normally magnetic. And just like nitrogen, each molecule of oxygen behaves like a tiny magnet when it's exposed to a magnet's magnetic field. Oxygen behaves differently than nitrogen, though. The way oxygen behaves is called paramagnetism. That's a fancy way of saying that each molecule of oxygen is attracted to a magnet's magnetic field. So, when I pour the liquid oxygen between the poles of the magnet, it sticks. And we can even make a little bridge out of liquid oxygen that'll stay there until the oxygen finally boils away.
Thanks for watching. I hope you'll join us again soon for another experiment.
Let's try that with liquid nitrogen at the same time.
Okay.
Ah, hey,
Ooh,
more. There's the good one.
Okay, I'm going to start this video now because all they're doing after this is playing around. So let me go back to, let me get out of this and go back to the PowerPoint. Okay, so when it comes to paramagnetism, as I said before, which is demonstrated in the video I just showed you, what is necessary as stated here is that the electronic structure of the particular species must have unpaired electrons. Let me underline that for emphasis sake. Okay, what's going on here? What? Oh, I forgot to plug back in my my tablet. Okay, so unpaired electrons. Once your structure has, once the electronic structure of the particular species has this feature, then it displays paramagnetism. So for example, in the case of sodium, where the electronic configuration for sodium is 1s2, 2s2, 2p6, 3s1. Here you have an unpaired electron in the 3s orbital. So therefore we know that sodium, we can predict that sodium will be paramagnetic.
Paramagnetic.
Exactly. So once you can identify an unpaired electron, all you need is just one, right? If you write out the electronic structure and then when you look at it, you see that there's at least one unpaired electron, then you know that your element or species, whatever it is, will be paramagnetic, all right? Okay, any questions about that?
Wait. Oh, not about the paramagnetism, but
Uh-huh.
didn't they use a extremely strong magnet to levitate a frog using diamagnetism? know-
That's an interesting one. I've never, I don't recall ever hearing of that before. I'm not saying it's
I
not
know-
possible because I guess it's possible. So I probably I'm going to look that up and see, but it's definitely possible because of course it depends on you know, what the composition is. And I'm quite sure that there might be some species within the frog in that case that would have unpaired electrons. So I would not put that outside the realm of possibility.
Hmm.
Yeah.
It was a magnet that I think it was the size of a dinner table or something. It was
Oh, okay.
massive.
Right. It's possible. I would not, it would not surprise me. Looks like an interesting experiment. I'm going to look that up to see, you know, how that's done. Okay. So that's basically it for today. Let me do the roll call thing. And you guys have some assignments that's due, I think, tomorrow. So make sure that you complete that. And of course, if you have any questions about that, I have office hours today from 2 to 5. And you can ask me any questions concerning that assignment. Okay, so today is the 1st of October. Okay, we're making good progress in this class because this is what, chapter 8? And I think we have like what, 3 more chapters or 4? Okay, so let me get out of this here. Oops, why did I do that? What in the world is happening here? Stop sharing. Okay, so let's see who's here. Arius, Rios, not here. Barber, not here.
Here.
Canon.
I'm
Oh,
here.
Barber. Oh, Barber is here. I'm sorry. My bad.
Sorry.
Canon, not here. Chang, not here. Chavis, not here. Clark,
here.
I see you. DeGraff, Not here. Franklin. Not here. Han. Not here. Hanik. Haron. Not Haron. Oh, Haron is here. Holland. Jurgensen. Rees. Rouse is here.
Yep.
Ronells is here. Santiago is here. And Smith. I don't see Smith, so I guess he's not here. Okay, so are there any questions, general questions or problems, issues before we leave? Well, actually, it doesn't matter because it's no one. Well, any questions? Any questions? No questions? All right, so
I
that's
don't
it for
think so.
today. So I'll see you guys next Tuesday. All right, so take care. Enjoy your weekend.
You
See ya.
too. Take care.
All right, bye.